Everyone, this lecture is an examples in DC to DC buck converter. This is the first example. We have 50 volt input voltage. We have the inductance 400 microhenry. The capacitance is 100 microfarad. The switching frequency is 20 kilohertz. The resistor is 20 ohms. First, we will analyze the circuit on point 4, and B, we will analyze it when the duty cycle is 0.8. So we will see how the duty cycle affects the output voltage, the maximum and minimum current, and the peak-to-peak ripple of the output voltage. So for number 1, V out, as we know, it's V input multiplied by D, and it's 50 multiplied by 0.4. This gives me 20 volts. And when the duty cycle is 0.8, it's 50 multiplied by 0.8. This gives me 40 volts. For B, to find the maximum and minimum current, we know that the maximum current is the output voltage multiplied by 1 over R plus 1 minus D over 2L multiplied by F. So I will get, for the first one, it's 20 volts multiplied by 1 over the resistance, which is 20 ohms, plus 1 minus 0.4 over 2 multiplied by 400 multiplied by 20 multiplied by 10 to the power minus 3. Since we have here kilo and here micro, so the remaining is 10 to the power minus 3. So the answer for this one is 1.75 amps. This is when the duty cycle is 0.4. When the duty cycle is 0.8, the maximum current is gonna be 2.5 amps. For the minimum current, for the 0.8, for the 0.4, it's the V output, which is 40 multiplied 1 over R, which is 20, minus 1 minus 0.4 over 2 multiplied by 400 multiplied by 20 multiplied by 10 to the power minus 3, and I will get a minimum current of 0.25 amps, and at duty cycle 0.8 I will get 1.5 amps. And if we look at the peak-to-peak ripple current, which is delta IL, I will get 1.75 minus, which is Imax, minus Imin. I will get here peak-to-peak ripple is 1.5. For the second one, the peak-to-peak ripple is 1 amps. So it appears that when the duty cycle go down, the peak-to-peak ripple current will increase. Now for the third point, we want to find delta V out. So we know that delta V out over V out will equal to 1 minus D over 8 LC multiplied by F square. So delta V out is equal to 1 minus 0.4 multiplied by V out, which is 20, divided by 8, multiplied by 400, multiplied by 100, by 10 to the power minus 12, multiplied by 20, multiplied 10 to the power 3 squared. So I will get a peak-to-peak ripple voltage for the 0.4 duty cycle. It will gives me 0.469%, and delta V out for the 0.8 duty cycle, it's 0.156%. So this is a better performance for the converter. Now I will go to the next example. The next example is to design, which is example number 2, to design buck converter the output voltage that is required is 18 volt. The load resistance is 10 ohm. The peak-to-peak ripple voltage, output voltage should be less than 0.5%, and the input voltage of the source is 48 volts. So I want this converter to operate under CCM, and I am meaning that the minimum current I want is greater than 0. Sorry, should be greater than 0. The duty cycle here is unknown. The L is unknown. The C is unknown. So I have to design all these things. But the switching frequency that I have is 40 kilohertz. So the question is, find also peak voltage ratings for each switching device. So let's start design the converter. First, number 1 is to find the duty cycle, D. The duty cycle is V out over Vn. And we have V out, which is 18. We have Vn, which is 48. So I get 0.375. Then I have to design the inductance that will makes the inductor work under CCM, and this inductor should be greater than 1 minus D over 2F multiplied by R. So this inductor should be greater than 1 minus 0.375 divided by 2 multiplied by 40 multiplied by 10 to the power 3 multiplied by the resistance, which is 10 ohm. So L should be greater than 78.12 microhenry. So I will multiply this inductance by 1.25. So I will get the minimum inductance needed for this converter is 100 microhenry. The next thing is in the designing process is to find C. For C, they said we want it to be greater than 0.5%, so it's 1 minus D divided by 2L multiplied by F squared multiplied by V out over delta V out. So I will get that C should be greater than 1 minus 0.375 divided by 2 multiplied by the inductor I've chosen is 100 multiplied by 10 to the power minus 6 multiplied by 40 multiplied by 10 to the power 3 squared multiplied by delta V out. V out over delta V out is 1 over 0.005%. So this turns out to be equal to, the C should be greater than 97.66 microfarad. So the minimum capacitance needed is equal to 97.66 micro multiplied by 1.25, the safety factor, which is equal to 120 microfarad. So I designed the L and the C for this converter. Then to find the switching voltage, since the voltage that appears across the switch, which is either the IGBT or the MOSFET, the voltage appears across its terminal. When it's on, the voltage is 0. When it's off, the voltage is Vn. So the peak value is Vn. So the peak value for the switch is the 48 volt. While for the diode, during the switch is on, negative voltage appear across its terminal. So it's going to be negative 48. Since the V diode peak is negative Vn, I will get negative 48 volt. So this is all about the designing of this converter. The third example, example number 3, the input voltage is 40 volt, D is 0.6, R is 15 ohms, C is 100 microfarad, F is 80 kilohertz, and number 1, find V out. So to find V out, it's Vn multiplied by D, so it's 0.6 multiplied by 40, I will get 24 volts. B, what is the average diode current? And if we look at the waveform of the diode current when the switch is on, it's 0. When the switch is off, the diode will start to conduct from a maximum value up to minimum, and then it will turn off. So here it's T, here is dt. So I have here maximum current, I have here a minimum current. So if I want to find this current on average, it's gonna be 1 minus D multiplied by V out over R, which is this is the resistor current. So ID is equal to 1 minus 0.6 multiplied by 24 over 15, which is equal to 0.64 amps. C, the question asked to find the average load current, which is the average inductor current. So it's equal to IR, so it's V out over R, which is equal to 24 over the resistance, which is 15, and this will equal to 1.6 amps. Or find the V diode. V diode will equal to minus V input, as we said, so it's minus 40 volts, and the waveform will equal to 0 during the switch is on, and minus 40 when the switch is off. This is D, this is DT. For E point, they want the minimum current that will make this converter works under CCM. So it should be greater than 1 minus D multiplied by R over 2F. So L should be greater than 37.5 microhenry. So if I multiplied it by 1.25, I will get 50 microhenry. Then they asked for the last point to find delta V out over V out, and this should be equal to 1 minus D over 8 LCF squared. So I will get here 0.156%. Another question is example number 4. Vn is 48, D is equal to 0.25, R is equal to 36 ohms, and what is the output power? The output power is IR squared multiplied by R, or it's V out squared over R. So it will be, the V out is Vn multiplied by D squared divided by R. So I will get 48 multiplied by 0.25 whole squared divided by 36. The output power is gonna be 4 watts. Next example is design L and C for a buck converter. The input voltage varies between 34 and 38 volts. The output voltage that is needed by the load is 12 volt. The switching frequency is 100 kilohertz. The output power of the load is between 10 watts and 100 watts. And the peak-to-peak ripple voltage is equal to 0.005. Design the converter under CCM. So we see in this example that the voltage is variable, the load is variable as well. So how to design LNC in such a case? So since the input voltage is less than 38 and greater than 34, and the output voltage is constant, which is 12 volt, then the duty cycle gonna be greater than V out over Vn and V out over Vn. So the duty cycle is going to be 12 over 34 and 12 over 38. So under this assumption, the duty cycle is between 0.316 and 0.353. The next thing that we have to take into consideration is the load resistance. The load resistance is, since P out is equal to V out square over R, so it's going to be V out square over P out, V out square over P out. So the resistance is 144 divided by 100 and less than 144 divided by 10. So I will get a load resistance which is greater than 1.44 ohms and less than 14.4 ohms. So to calculate L and C, I will take the maximum resistance value and the minimum duty cycle. Why I will do that? If we look at the inductance that is needed to be found for the CCM operation, it's going to be 1 minus d R over 2F. And since d and R are variables, what makes this value to be maximum is when d is minimum, and what makes this maximum is when take R as maximum. So L should be greater than 1 minus 0.316 multiplied by the maximum value for the resistance, 14.4, divided by 2 multiplied by 100 multiplied by 10 to the power minus plus 3. So L should be greater than 49.2 microhenry. So the minimum inductance multiplied by 1.25. So I will get a 70 microhenry. Now to find C, C should be greater than 1 minus D over 8L F squared multiplied by V out over delta V out. So it should be greater than 1 minus 0.316 over 8 multiplied by 70 multiplied by 100 multiplied by 10 to the power minus 12. So it's 70 micro multiplied by 100 mega, so they will cancel each other. So this multiplied by 1 over 0.005, I will get C greater than 24.4 microfarad. So C, after multiplying by the 1.5 safety factor, I will get 30 microfarad. So we designed C and L that will makes this converter operates under CCM. The next question is, or let's say example number 5. We have been given the minimum current, which is 4 amps. The output power is 25 watts. The resistance is 1 ohm. The switching frequency is 100 kilohertz. The average value of the switching current is 2.5 amps. And they asked us to find L under this condition. To find L here, L should be greater than 1 minus D over 2F multiplied by R. I have R, I have F. The only thing that is missing is D. And D is equal to V out over Vn. I don't have V out or Vn, but I have the power. The power is V out square over R. So V out is equal to R multiplied by P under the square root. So V out is equal to square root of 25, which is 5 volts. But this is not enough to find D. I can find D by using either the maximum value or the minimum value of the input current. So I will use the minimum value current since I have it here in this equation, in this question. So I min is equal to V out multiplied 1 over R minus 1 minus D over 2LF. So this one is unknown, this one is unknown. So how to find D? In the question I have been given the average value of the switch current. So if I have drawn it during on this, there will be a current here flowing through the switch, and during off it's 0, and this is the same as the average value of the switch current is equal to the average value of the input current. So the average value of the input current will be equal to 2.5 ampere. So the duty cycle is the input current on average divided by the load current, and the load current is equal to the output current multiplied by V out multiplied by R. V out is 5 multiplied by R, which is 1, so it's 5 amps. Now D is equal to 2.5 divided by 5. I will get to the cycle of 0.5 or 50%. Now I will substitute this in this equation, since now I have only one unknown, which is L. I will use this equation. So I min is 4 equal to V out, which is 5, 1 over 1 minus 1 minus 0.5 divided by 2L multiplied by 100 multiplied 10 to the power 3. Yeah. So now, after manipulating this equation, I will get L equal to 12.5 microhenry. I hope all the examples that I solved in this lecture help you how to design the buck converter, and stay tuned to the next lecture, which is going to be about the post converter. Thank you very much.